Greetings from Baltimore, everyone. Having seen the discussion at Discord around p-value, I decided that I should probably go ahead and provide this video about p-values. So forgive me for the lesser quality, as I don't have all my equipment with me since I'm traveling. But what I do want to help you make sense of is an initial understanding of p-value from a perspective you may not have ever seen before. So the first thing that I want to do is I'm going to go to this program called TI Nspire. It's a program developed mostly for high school and maybe undergraduate math courses, this particular version at least. It has some really cool features that it can handle with statistics. So the first thing I want to show you here, I'm going to use this data set that includes the number of residents in each of the world's 1,000 largest cities. At least this was true in 2008. So it's changed since then, obviously. But I want you to take a minute and look at this distribution of the number of people in these cities. So as you're watching this, just maybe hit pause for a moment. I want you to think about how would you describe the center, shape, and spread of this distribution here. So as I look at this, I see a very sharp decline towards a tail on the right side, which indicates a right skewed distribution. Definitely not symmetric, definitely not normally distributed. Also, if we were to sort of estimate where the center was, the mean you can think of as a balancing point where the taller the bar is, the heavier the bar is. So if you think about that, if you were to put your finger somewhere along the axis here at the bottom, about where do you think the center would be? I'm thinking maybe somewhere in this general area here is probably where it would be. And because of these cities that are way out here, you could barely see this bar sticking up here, which is, if these are, so 2e plus 6, that means 2 times 10 to the 6, so 2 followed by 6 zeros, so that's 2 million. So this is really, really big out here. 1.2 times 10 to the 7. So you're looking at really, really big numbers there. These are going to pull up that mean for sure, and so the median is going to be a little to the left. The mode obviously is here between 0 and 1 million. 686 different cities there. So out of 1,000, that's quite a lot. That's more than half of the world's 1,000 largest cities in this one bar. So if you're thinking about a box plot overlaid on top of this, that's more than 50% right there. But the mean and the median, the mean's going to be a little bit to the right, so the mean may be in this bar, the median may be in this one. Just to get an idea of this distribution, and this is population data. This is not a sample. This is, if we keep the context for 2008, this is what the world's 1,000 largest cities populations were. All right, so let's suppose for a moment that you were tasked with trying to estimate what the 1,000 largest cities populations average was. What is the average of the world's 1,000 largest cities? The average population for the world's 1,000 largest cities in 2008. And for whatever reason, you decide you don't want to just go and find those 1,000 largest cities. Maybe it's something that's unknown at the time or something like that. Let's just play with that idea to motivate this. So then you can look at this and think, okay, well, I could just go to 5 of these cities and pay someone there to do a census. Let's say that that's what you have money to do. So, well, let's see what happens when we do that. If we draw a random sample of 5 cities from the world's 1,000 largest cities. Now, first of all, this sort of sounds absurd, right? Like, we're going to estimate the world's 1,000 largest cities with a random selection of 5. That just sounds like a bad idea. And you're right, it is. But what I want to point out here is something that's really important in statistics. So just stick with me for a little bit. So if we actually go to this here, all right, so in the top left corner of the screen, you can see these are the actual populations of the 1,000 largest cities, and then you have the city name here. And what this spreadsheet is going to do is, as I refresh this page, in the bottom left corner of the screen, you're going to see selections of a sample of 5 plotted. So right now you see this is a random, completely random selection of the 1,000 cities in this list in the top left section. So right now you see here's a city that had around 640,000 people, and this one was 394,000. Notice the scale. It's from 0 to 1.2 million. I'm sorry, that's 12 million. Then we have in the top right corner, this is the actual distribution of the 1,000 largest cities, all 1,000 of them you can see here. So it makes sense that with a selection of 5, you might get some that are clumped closely together. It looks like they range from just under 400,000, with the largest one being a little over 800,000, getting closer to 850,000. So as you think about that, you're going to see on the right side the mean of the 5 points plotted. So this bottom right graph is going to represent the means of all these different random samples of 5 that we pull out one at a time. So if I can remember how to do this, let's see what I said here again. Command R. So I just refreshed it, and you'll see that a point was added in the bottom right. This point way over here. That's it's actually showing it not as an approximation, but you can see that it's getting close to about 2 million. This is 2.4 million here. This is 1.8 million here. And you can see, look at the distribution of these 5 points. So earlier they were all clustered really tightly together, and now it looks more skewed, similar to what the picture looks like for the entire population. However, we still don't have any points that are really far out here, around 12 million, but at least it looks more similar to what the actual population of these cities looks like, which is what we want. We want to have our data be representative of the population, so it should look like the population. In this case, we're sort of inventing this. In reality, we wouldn't know what it looks like. And as I continue to refresh this, just keep an eye on the bottom left and the bottom right, the 2 graphs on the bottom, and you'll notice that sometimes the points are really clustered together like it is right now, and sometimes they're more spread out, which means that there's relatively small amount of consistency in the types of samples that you get. And as you watch the distribution get filled on the right side, as you see that graph be generated, you start to notice that it's looking sort of skewed. And at first thought, you might be thinking, well, that's what we want, right? I mean, the population is skewed. We want it to look like the population. Well, maybe not in this case. I mean, think about it. The whole purpose of selecting a random sample of 5 is so that we can estimate the mean of the population. So we want the mean of the 1,000 largest cities at this point. which we know is probably around between 1 and 2 million somewhere. Um, so think about it like this. When you take a random sample from the population, your goal is to target the population mean or maybe some other statistic that you're interested in. So imagine throwing darts at a board. If you want to get good at hitting a specific place on the board, it doesn't necessarily have to be the bullseye, but if you're trying to hit a specific place, you want your throws to be consistently close to that place. And if they are really close to that, sometimes they might be a little bit above, sometimes they might be a little bit below, sometimes they may be a little bit to the left, a little bit to the right. But in general, you want things that are tightly clustered around that point. In other words, imagine yourself throwing darts and you're trying to hit the bullseye, but you consistently throw to the right of that. That's not very good because you're not actually getting close to the target. And there are other ways that you would need to adjust what you're doing in order to make sure that you are getting close to that. So it's similar here with this sample means. What this is showing is that there's a lot of data that's being clustered out here to the right. There's this tail, which tells us that we're not being very consistent in how these samples of 5 are actually representing the population. Sometimes we see that they're tightly clustered, maybe close to where we would hope they would be at this point, this area here. But then sometimes they're really, really far off, way out here in the 3 million population size range. You don't want to see that. In this case, symmetry is a really good thing. And when it's symmetric and tight around the center that you're trying to target, that is the best situation. So with random samples of 5, as you might guess, there's a lot of variability in its ability to target the population. All right, so obviously, as you would have guessed before we started this, a sample of 5 is absurd to begin with when we're trying to target something that has 1,000 people in it. And as we could see, that was a bad idea from the data we collected, this empirical data that we collected. Okay. So what if we raise the sample size to 20? So let's continue to create some things. So I'm going to go a little slower at the beginning here. You can see in the bottom left, there's a little bit more consistency with things more frequently, at least, looking like the population in the sample, which is what we want, the distribution to be similar to the population data. And on the right side of the graph, things, at least at this point, seem to not be quite as spread out. So I'm going to speed this up a little here, and you'll notice that this graph being generated of the sample means, the means of the samples on the left, the bottom left, there's still some slight skewness to this. However, we've collected quite a lot of data at this point, and it doesn't quite go as far out. A little bit of skewed, and it's a little more tightly clustered around the 1 million range here than the previous graph was, if we go back to that. So the graph has been shifted a little bit to the right. So both sides, the minimum has gone up and the maximum has come down. And so there's less spread. Seems to be more tightly clustered. So this is better. It still will give us a better idea of what the average of the world's 1,000 largest cities would be. Now, what happens if we then go to, say, a sample size of 100. Now remember, we're estimating the world's 1,000 largest cities. A sample size of 100 is 10% of that. So let's look at what happens when we do this. And of course, the bottom left, there's a lot more data values. It consistently looks much more like the actual population data, skewed to the right. It's still not quite as skewed, which you're never going to see it like this all the time. There's not many points that are really far out here on the far right of the population graph. So I'm going to hold this, speed this up a little. And as you see these be generated, you'll notice that it's a lot more tightly clustered. If we think about the mean of the sample means plot in the bottom right, those green dots, things are much more close to it, which tells us the standard deviation is going to be much smaller. The average deviation from the mean, from the center, is going to be smaller. This is a good sign. It means that if we were to take only one sample, which is what we would do in reality, we are more likely to get closer to the true average of the world's 1,000 largest cities than if we had used a sample size of, say, 20 or 5. There's still a chance that we will get farther away than those. It's just gives us a much better chance of getting something closer to the true population we're trying to target. All right. So let's look at something else. First of all, this plot here in the bottom right is called a sampling distribution. A sampling distribution is theoretical. It doesn't exist in reality. You're never going to take hundreds and hundreds of samples from the same population. If you were going to do that, you would just get a bigger sample from the population to begin with. So if you can get 900 of the largest 1,000 cities in the world, you're in a pretty good place, for instance, as opposed to collecting just these samples over and over and over again. And a sampling distribution is the means of all the possible samples that could exist of the size of sample that you've collected. So technically, it is infinite number of samples. However, if that bothers you, just think about it as all the possibilities that could exist. And this idea that we've just looked at is called the central limit theorem. And the central limit theorem says this, that the sampling distribution, as the sample size increases, will look closer and closer to a normal distribution. The larger the sample size, the more the sampling distribution will look like a normal distribution. And notice that's not true for a sample size of 5. Look at how skewed it looks. Actually, that's a sample size of 20. Even the 20 looks skewed. The sample size of 5 looks even more skewed. So as the sample size increases, it starts to look less and less skewed, which is good when you're trying to get closer and closer to a specific target, in this case, the mean of the population. So it doesn't mean that the sample that you collect will look more normal. As the sample size goes up, your actual sample distribution, which is the bottom left picture, the random sample that you collect is going to look more and more like the population does. But the sampling distribution will look more and more like a normal distribution, which gives us more reliability in our prediction. All right, so in this particular case of a sample size of 100, first of all, the population data, the 1,000 largest cities, has a mean of 1.15 million, with a standard deviation of 1.5 million. So that is a really big standard deviation, just as we may have guessed, because there was so much skewness involved. There was a few big outliers. And if we look at the sampling distribution, this green picture here, and we think about that, the sample means, the mean of those sample means is 1.15 million. The standard deviation is much lower. This is what we want. So we want the mean to represent, be really, really close, if not identical to the mean of the population we're trying to target, which happened. And we want the standard deviation of our sampling distribution to be really small, which tells us that we can feel more like we get a reliable read on the population, that our prediction about the population is going to be reliable. You'll see here I had put in 465 random samples of size 100 from the list of 1,000. And let's take a look at a couple of things here that may help us. So A minus B, what is this doing here? Well, it's taking the mean of the sampling distribution and subtracting one standard deviation from it, which puts us at, so the mean is at 1.15. If we go one standard deviation less, we're at about 1 million, and go one standard deviation above, we're about 1.3 million. And if we, let me take this out. If you do that, you get about 308 of the 465 sample means. So within one standard deviation around the mean, which is really tight, it's between about 1 million around here up to a little bit over 1.2 million here. That one standard deviation is encompassing 308 out of the 465. So 308 out of 465, 66% of the sample means are located within one standard deviation of the mean. By the way, this is accurate to what happens in theory when things are normally distributed. You get about 68%. If it was perfectly symmetric, and imagine thousands of data points, you get about 68% of the data contained within one standard deviation, plus or minus one on each side. If we go 2 standard deviations away, that's 445 of the 465. So let's see what that would be. 445 of the 465 data points is 95.7%. This is extremely accurate to what it is in theory. In theory, it's a 95% within 2 standard deviations. And if we go out 3 standard deviations, this is where things become rare. They become really far away from the mean. That's actually 465, so it ends up being 100%, which in theory, within 3 standard deviations, if there are, imagine, thousands of these data points rather than only 465, it is 99.7% about of the data. So you can see that when sample sizes are big, we get really a lot more accurate reads on what the population will be. Now let's look at something else here. So what I've done is I've taken the sample means of a similar sample from a previous iteration of this, and I've created a Z-score. Now we haven't talked about Z-scores yet, but what a Z-score does is it tells you how far an individual data point is from the mean in terms of the number of standard deviations. This is helpful sometimes to be able to tell how far something is. So if we think back to here, we were thinking about things that were 1 and 2 and 3 standard deviations away from the mean. So what if you're talking about a specific data point? If a specific data point is 3 standard deviations away from the mean, that is really far away in terms of when you think about it in relation to all of the rest of the data and in relation to the mean. So if we do that with every single one of the sample means here, this is what the data is going to look like. So on the top you see the sample means, all spread out here between around 850,000 up to 1.6 million-ish. And the bottom graph represents the z-scores of those values. And the z-scores of those values are not, notice that the distribution looks identical. It doesn't change how spread out it looks as long as you keep the scaling the same. It doesn't change the location of them, it simply redefines what these mean. So for instance, notice here there's a 0 in the middle. Well, that 0 is there because if it's 0 standard deviations away from the mean, then that means it is the mean. Does that make sense? I can make another video about z-scores if you want to. And you can see the formula here at the bottom. You simply take the actual data point, in this case the sample means, and you subtract the mean or the average from it, and then divide by the standard deviation. I may have to go back to some 4th grade math here and think about division again. In division, let's say you're dividing 6 by 3. Conceptually, what you're thinking about is how many groups of 3 are there in 6? And that's how you get 2. 6 divided by 3 is 2 because there's 2 groups of 3. Well, in this case, the numerator here is the distance that a point is from the mean, and you're saying how many groups of a standard deviation are there in that distance? How many standard deviations are there between the mean and that value? That's all a standard deviation is. It's a rather simple equation. So what I want you to think about for a moment is, so these represent sample means. So here's a data point out here on the right. And this data point, which if I hold this up here is a little bit more than 1.6 million, is about 3 standard deviations away from the mean, which we know is a long ways from the mean, relatively speaking. So let's say that you take a single sample from the data set here. You're only going to do this once, remember? Going back to our original goal to estimate the population, the average of the 1,000 largest cities in the world. And you're only going to take one sample, and you're going to take a sample of 100. And when you do that, you happen to get this data point way out here. So, knowing what we know at the moment, that data point is in reality 3 standard deviations away from the mean. What does this tell us? So remember, within 3 standard deviations is 99.7% of the data that's possible. So if we collect random samples over and over and over again, we know 99.7% of them are going to be within 3 standard deviations. Now that leaves 0.3% left, and only half of that is on the right side here, where this specific data point we're looking at is. So that leaves us with 0.15% of possibilities of getting a random sample from the 1,000 that is as extreme or more extreme. So right now you don't see anything beyond that, but if we were to continue taking random samples, eventually something would pop up over there. It may take thousands before that happened, but it eventually would, just by chance. So now you're left with a question. If you were to know this, that this one data value that you have is 3 standard deviations away from the mean, telling you that there is a 0.15% chance of getting that specific sample that you got, do you believe it? You have 2 options. One of them is to say, I think that this data value is too far away from the mean, and I didn't get it just by chance. That you tried to get a sample that was representative of the population. So you can trust that your data value out here at 3.197 standard deviations from the mean is accurate, and that you don't think you were lucky enough to get something that's that far away by chance. If that's the case, you're going to reject the notion that the true sample is at around 1.15 million. Instead, you would say, I trust my data, and I think the actual population is really more around 1.6 million for the 1,000 largest cities in the world. The other option is to say, no, I think it's actually plausible for whatever reason. Maybe you don't think that you did a good job for whatever limitations may have existed in getting a representative sample. So you aren't very trustworthy, and you would not, maybe 0.15% chance is not good enough. Maybe you would rather see that number be a lot smaller. Okay, now we're talking about p-value. This percentage chance of getting the sample that you got, of getting something as extreme or more extreme than what you actually got, that percent is a p-value. And what we've done here is simulate the p-value. In reality, what you would do is base your understanding of what those percentages are on the theoretical distribution of the sampling distribution. And then the percentages would be calculated from that, which is based on the sample size that you have. So if we were to do this thousands and thousands of times, our actual data points here would approximate what the theoretical distribution is for the sampling distribution. And those theoretical distributions are what are used in order to ultimately calculate a p-value. And if you're familiar with calculus, this involves taking integrals under the curve by pinpointing the exact location of the sample mean that you have on this sampling distribution here. Okay, so that is a brief introduction to p-value, and I think it's important to keep thinking about this. So let me know, go into Discord, talk about p-values in there. Let me know where you're struggling with this, what you still need to understand. I think it's extremely important to understand this because this is the type of limitation that we're talking about with that ASA statement. It can only say so much. And that so much is also based on other limitations that exist and the assumptions that we're making about what that p-value actually is telling us. So keep thinking about this as we move forward into thinking more about a t-test soon, which p-value is essential to understand in order to make decisions about t-tests. So pop back into Discord after you watch this. Let me know how things are going, and we'll continue this discussion.